So I thought it would be good to go through just a nest of examples so we could see kind of what divergence and curl look like in the plane for sort of simple or common vector fields. So for this first one here, Cx, Cy, if we sketch this, this is actually just this is the same thing as if I denote the vector x comma y by boldface x like this, then this one is just c times that vector. So in other words, wherever you are, you just point away from the origin by that as much as the point that you started at. So it looks like this. So the further you are from the origin, the bigger the arrow. Anyway, so there's a little sketch. Okay, so let's look at the divergence. So for the divergence, we do ddx of this part, which is c, plus ddx of this part, plus ddy of this part, which is also c. So we have 2c for the divergence. And you can see it looks like if I were to evaluate at any particular point, there's more stuff coming out than there is coming in. So that would be positive divergence. Okay, and I guess I drew the picture thinking that C was positive. Sorry, I should have specified that. Yeah, let's say that. This is for C positive. Okay. What about the curl? So for the curl here, I'm going to do partial of this one with respect to x, so 0, minus the partial of this one with respect to y, which is also 0. So I have 0 for the curl over there. And so if you have some path traveling through here, basically it's going to be about the same on either side sort of that vector and or of that curve. So there's not going to be any expansion. Or sorry, not going to be any curl. Okay, for the other one, we plotted this guy once before. It looks like this, but as it's sort of rotational. But as you get further out, they get bigger, right? So now this one looks obviously like it's going to have a positive curl, and it does. And so that's let's see, when we do this one with respect to x, we get c. Then we subtract the partial of this one with respect to y, so minus negative c, so we get a plus 2c for that one. And it's sort of immediately makes you think that there's going to be a rotation because you see the rotation around the origin. That's definitely positive, but it's actually 2c everywhere. And so if you're out at some other location like this, you can see, just like I was talking about with the river example before, the arrow on the left is smaller than the arrow on the right, and that's going to cause a net tendency to rotate around counterclockwise, and that's true anywhere in this space. If we look at the divergence, let's go back and compute the divergence. We need the partial of this one with respect to x, which is 0, plus the partial of this one with respect to y, which is 0. And so then we have 0 plus 0 is 0. So that one has divergence of 0. Let's look at this one. So for this one, our x coordinate is given by y. So the amount of horizontal motion depends on how high you are. So along the x-axis, where y is equal to 0, there's no motion. But if we go up to oops, wrong tool. Here we go. If we go to this line here, where y is equal to 1, then we're going to have 1 comma 0. So that's pointing straight to the right. So it's going to be like this. If we go down, it's going to be pointing 1 to the left because we're at negative 1. If we go up higher, it's going to be pointing faster. So we have some kind of vector current that looks like this. So, thoughts about divergence and curl? Well, if we go ahead and compute it, let's see. So partial of this with respect to x is 0, and that's definitely 0, and so we get 0 for divergence. When we go to compute curl, we have partial of this one with respect to x, minus partial of this one with respect to y. So that's minus 1. So minus 1. And so like you can see that if I have a point here, the current is moving faster on top than on the bottom. So it's going to cause a clockwise rotation. And down here as well, the current is moving faster on the bottom than it is on the top. So it's going to cause a clockwise rotation. So this is why we have a minus 1 going on here. So this one we would call, probably call it a shear. I guess the first one would be, I'm sorry, the one above that, this is some kind of rotation. And this other one that we have, this is some sort of source. Whoops, source. Okay, then we have the magic vector field. So this is the one that speeds up as you get towards the origin. Something like that. And so the nifty thing about this one is that it speeds up at a rate so that it's sort of balanced between what's happening on either side of you with the rotation. Sorry, that was garbage. Let's just delete that and start over. So let's compute the divergence. So the divergence of f in this case is going to look like, let's see, so we differentiate the first one with respect to y, with respect to x, and there's no x's in the numerator, so we just have the piece from the denominator, and we end up with 2xy over x squared plus y squared quantity squared minus 2xy over x squared plus y squared quantity squared. So the divergence actually ends up being equal. If we go to compute the curl of f, we actually already did this. It's the computation to check whether or not it's exact. Maybe you noticed curl is equal to 0 if and only if it's exact. So irrotational is the same thing as being exact. So we end up with y squared minus x squared over x squared plus y squared quantity squared minus itself. I will spare you a repeat of that conversation, so it's this one. So and so even though it looks like it's rotational, it actually isn't. Then let's see. So this one is the we call this the vortex. Faster and faster in the middle. Okay. And then for this last one, we just have some random thing. Let's go ahead and compute it. I don't really know or care actually what this one looks like. It's nothing in particular. But if we compute its divergence, we get 2xy from the first part plus 3, taking the partial of 3y with respect to y. And then when we take the curl, let's see, so we take ddx of the second component, and then ddy of the first component, so that's x squared, and we subtract it. Okay, so you can see we have, here are some examples, well actually, here are some examples of incompressible vector fields, and then we also had some irrotational vector fields here, and here we got some zeros.